Download this code from codegive.com, link in the description below. Python incorrect Boolean checking for prime numbers, a deep dive, with Stack Overflow inspiration. Prime numbers, those integers greater than 1 divisible only by 1 and themselves, are fundamental in number theory and computer science. Determining if a number is prime is a classic programming exercise. However, seemingly simple solutions can be plagued by errors, particularly in how Boolean logic is applied. This tutorial explores a common pitfall, incorrect Boolean checking in prime number algorithms, using inspiration from real-world examples often found on Stack Overflow. Why is prime number testing a good example? Prime number testing neatly exposes Boolean logic issues because 1. It involves iteration. Prime checks typically involve looping through potential divisors. 2. It relies on a conditional exit. You often want to exit the loop early if a divisor is found. 3. Boolean flags are common. *is_prime flag is frequently used to track the primality status. The common pitfall, prematurely setting is_prime to true. Let's start with a flawed code example that demonstrates the issue. Why is this wrong? The crucial error lies in the else block. This line is executed every time a number I is not a divisor of n. Therefore, the is_prime flag is constantly being reset back to true if the last number checked isn't a divisor, even if an earlier number was a divisor. Consider the case of n equals 4. The loop executes twice. 1 I equals 2, 4% 2 equals 0 is true. Is_prime is set to false. 2 I equals 3, 4% 3 equals 0 is false. Else is executed. Is_prime is set back to true. The function incorrectly returns true because the last non-divisor, 3, overwrites the earlier discovery of the divisor, 2. Stack Overflow inspiration, searching for similar issues. Imagine you encountered this problem and went to Stack Overflow for help. Keywords like Python prime number Boolean incorrect, Python prime Boolean flag wrong, or Python prime algorithm wrong would likely lead you to discussions with similar issues. You'd find questions and answers highlighting the flawed logic of unconditionally setting is_prime to true within the loop's else block. A corrected version, setting is_prime only once. Here's a corrected version of the code. Key improvements *. 1. Removed the else block *. The crucial change is removing the else block that was incorrectly resetting is_prime. Now, is_prime is only set to false when a divisor is found. If no divisor is found throughout the loop, it remains true. 2. Added break *. Once a divisor is found, there's no need to continue checking. The break statement exits the loop, improving efficiency. An even more efficient version, checking up to the square root. A fundamental optimization in prime number testing is to check only up to the square root of n. If a number n has a divisor greater than its square root, it must also have a divisor smaller than its square root. Improvements *. 1. Square root limit *. The loop now iterates only up to sqrt, n, significantly reducing the number of iterations, especially for large numbers. 2. Early exit *. The function immediately returns false if a divisor is found, and only returns true if the loop completes without finding any divisors. Boolean logic best practices for prime number checking *. Initialize correctly *. Start with a reasonable assumption, usually true if you're looking for a positive outcome. Only set to false if a negative condition is met. The is_prime flag should only be set to false when a divisor is found. Avoid indiscriminately setting it back to true within the loop unless you know the logic is correct, which it usually isn't in this scenario. Use break or return for early exit. Optimize your code by exiting the loop or function as soon as you determine the number is not prime. Test thoroughly. Use a variety of test cases, including small primes, composite numbers, and edge cases, like 0, 1, and 2, to ensure your code is working correctly. Beyond Boolean flags, alternative approaches. While using a Boolean flag is a common approach, other methods exist. Consider this concise version using the all function. This code uses a generator expression, n% for I in range, to create a sequence of remainders. The all function returns true if all elements in the sequence are truthy, i.e., non-zero remainders, meaning no divisors were found, and false otherwise. While elegant, it can be less readable for beginners. Debugging strategies. If you're encountering issues with your prime number algorithm, these debugging techniques can help. Print statements. Insert print statements within the loop to track the value of I, n%, and is_prime at each iteration. This allows you to visualize the flow of execution and identify where the logic is going wrong. Debugger. Use a debugger, like those available in IDEs like VS Code or PyCharm, to step through the code line by line, inspect variables, and set breakpoints. Test cases. Create a comprehensive set of test cases, including edge cases and known prime and composite numbers. This helps you identify the specific scenarios where your code fails. Rubber duck debugging. Explain your code to an inanimate object, like a rubber duck. The act of verbalizing your logic can often reveal errors you might have missed. Conclusion. Prime number testing is a valuable exercise for honing your programming skills, particularly in Boolean logic and algorithmic thinking. By understanding the common pitfalls, such as the premature setting of Boolean flags, and by applying debugging techniques, you can develop robust and efficient prime number algorithms. Remember to leverage resources like Stack Overflow to learn from the experiences of other programmers and refine your solutions. Don't be afraid to experiment and test your code thoroughly to ensure its correctness.